Alright, so let's do the question 62. The 62 has a two parts problem. Find the electrode potential for each one of these half set. So let's do that one. So if we, first one is that Fe3 plus electron is becoming Fe2 plus. That's the one reaction, and the standard potential for that is given by, can't really read this stuff. What is this thing? Fe3 plus. Oh, right here. It's right here. So it's 0.771. Alright, so it's 0.771 positive volt right here, right? And then this is at the standard conditions, and we are not really talking about the standard conditions here, right? Because the concentration of Fe2 plus and then Fe3 plus is not the same here. So let's use the formula that's given in the all the way at the bottom, which is this one right here, 19.6. So E naught minus RT. So E is equal to E naught minus RT over NF ln of Q. So for this particular case, E naught is this one. So let's just write out everything in one shot. So for the cell 1, we have equal to E naught is at 0.771 minus number, the R is 8.314 multiplied by 298.15 divided by number of electron is 1. So 1 divided by 96500, that's Faraday's constant, multiplied by log of Q. Q right here is a product over reactant, right? Product concentration is Fe2 plus, which is 0.1, divided by the reactant concentration of 1, which is Fe3 plus concentration. So all of those things is done. Let's get this one. Alright, so let's do the cell number 2. Cell number 2 is actually the MnO3 MnO4 minus, somehow becoming Mn2 plus. So we can actually use the table here. So let's just figure out what the table says. You can actually balance it by yourself, but I'm just too lazy. I don't want to do it. So it's this one right here. So all of these things, it's 1.52. The cell potential is 1.52. I'm just getting it directly from the table, right? No change whatsoever. Now let's do this one. So it's equal to, I should probably write out the entire thing, right? Let me just try to write out the whole thing. Can I actually snip this thing? Yeah. It's much better. Alright. Not much better. So now equal to E naught is 1.52 minus 8.314 multiplied by 298.15 divided by number of electron, that's 5, right? Divided by 96500 multiplied by ln of the product over reactant. Product has Mn 2 plus, that concentration is given by 1e to the 1e negative 4. That's it, right? Now we don't care about the liquid. And then the reactant is Mn4 minus, which is this guy right here, and this one right here, which is 1e negative 2 multiplied by, we have a H plus, right? 8 of those guys. So 1e negative 3, I'm just trying to get that, 1e negative 3 to the power of 8. Remember that coefficient of 8 means that it's a power of 8, right? So that to close out all the reactant, and this to close out the natural log. And hit enter, we get that one right here. So these are the each cell potential. So that's the part answer to the part A. So let's do the part B here. Calculate the overall cell potential. Remember that cell potential formula? Cell potential formula was cathode minus anode, right? So let me just try to write that. E cell is equal to E cathode minus E anode. So we have to figure out which one actually produce the electrons and which one is going to eat up. So for this particular case, which one is the reaction is going? Reaction is going Fe3 becoming Fe2, and then mangan 04 becoming mangan 2. So this one right here is going to eat up the electrons. So this means that it's going to be a cathode, and then Fe3 becoming Fe2. This is also cathode too, but which one is stronger cathode? It's this one, right? So for that reason, that's going to be 1.52 minus, no, not 1.52, is equal to this minus that. Just the difference. Because I'm not completely sure which one is the cathode and which one is anode for this particular stuff. It really doesn't say. It looks like it's going to be the same, going in the same direction. So yeah, in that case, that's pretty much all I can say.